As you're following these presentations in the order in which they were intended to be watched, you'll get total immersion into really demanding three-dimensional visualization at this stage. I hope that is not going to cause you overload. Remember that very similar to what we did with vector-valued functions, we will revisit these ideas over and over again, and just by setting the stage and having everything in our minds already, these kinds of things will become less complicated with time. If you wish, this is also a presentation that you may want to watch again when we actually start working more heavily with parametric surfaces. Right now we're just going to look at the geometry. Okay, so why would we want to work with parametric surfaces? Basically, the idea is that we want to model surfaces in space. And if we do that, well, we realize that graphs of functions of two variables are surfaces, but not all surfaces are graphs of functions of two variables, and that is because graphs of functions of two variables satisfy a vertical line test, right? When you've got a graph, you've got the domain underneath, and so you go up to the graph and then over to get the z-coordinate that gives you the output of the function. And if you have something like a sphere, well, a sphere doesn't satisfy a vertical line test, because unless you've got a line that is tangential to the sphere, every line either intersects that sphere not at all or twice. And so that means we need another idea to model surfaces in three-dimensional space. And basically, we already know how to model paths in multidimensional space, and we have seen with functions of two variables that if we put a bunch of paths together, we can get a surface. And so that really is the idea behind the definition of a parametric surface. And so we talk about now a vector-valued function of two variables, s of u and v, surface of u and v. That is a function that maps each point uv in its domain to a vector surface or surface point of uv. And for the vector-valued function of variables suv with domain d, the set of all points for which there is a uv in D, so that S of uv is the position vector of P, is called a parametric surface. And so basically what this is, again, we are going to interpret these vectors as position vectors to get the parametric surface. And for vector-valued functions of one variable, we had a one-dimensional domain, we got a one-dimensional image, we got a curve. With a two-dimensional domain, where we've got two directions, u and v, we get a two-dimensional object in three-dimensional space, and that's a surface. So, yeah, and the component equations of those things are also called the parametric equations. I'm already into the visualizations here. Namely, if we are looking at u and v, well, then here's our domain. And our function s of u and v is a function that maps this domain into three-dimensional space, and what it does is it takes this flat surface and turns it into a sheet in three-dimensional space. And the connection to vector-valued functions is that, okay, here's the surface. So if we hold u constant, well, we get straight lines in the domain. And when we hold u constant, well, we get vector-valued functions of one variable, namely s of constant and v, and those become curves in three-dimensional space, and those are the curves for u equals constant. Those curves typically form a grid on the parametric surface, together with the curves that we obtain when we hold v equals constant. Whoops, I jumped to the wrong place. So if we hold v equals constant, we get horizontal lines. And, well, s of u and constant, those are then, again, curves in three-dimensional space that go on the surface the other way. Those are the curves for v equals constant. And so that means we can use what we know about vector-valued functions of one variable to generate this grid of curves on the surface. And as soon as we have that grid, we have the whole surface. And in fact, in exactly this fashion, surfaces again are produced by computer algebra systems. A computer algebra system basically plots a grid and then interpolates that grid. And we're also going to see that in pictures and in animations. So to draw a parametric surface, basically you draw lines where v is constant and you draw lines where u is constant in the domain. And these lines translate into vector-valued functions into parametric curves in the image. And these curves can be interpolated, and once they're interpolated, we end up with a surface. And yeah, the other part that I just sort of jumped over, when people talk about vector-valued functions of two variables, they also talk about parametric equations. And just like for vector-valued functions of one variable, those two are the same, two sides of the same coin. Namely, if I've got a description, surface of u and v is something in x, something in y, and something in z, well, that's easily translated to parametric equations. X of u v equals something for x, that same something, namely y of u v being what we have for y, and z of u being what we have for z, and of course vice versa. If I have these parametric equations, I can just put them into a vector to get the vector-valued function. All right, so what I'd like to say here, even though this is now a quite demanding visualization, we're there. Because parametric surfaces can be used to describe any surface in three-dimensional space. That means three-dimensional environments, for example, in computer games, are generated by rendering a bunch of parametric surfaces. Now, sometimes that is done with polygons and not with such fancy surfaces as we're going to see here, but basically, parametric surfaces can be used to describe anything. In physics, especially in electrodynamics, I think, they are called Gaussian surfaces or test surfaces, and they can have various shapes. Typically, physicists use, I think, spheres and maybe cylinders. You're going to see that in physics, but technically we can describe any shape we want, and that is nice. The specific techniques will get very detailed. Like I said, for example, in computer games, they use polygonal approximations for your surfaces, and that is something that gets very detailed, and the number of surfaces needed to describe, for example, a face in the rendering for a digital movie, that can be a large number of surfaces, but again, at its very heart, it has this idea. And so what we want to do is we want to take a look at some, and I want to emphasize, simple examples and simple techniques to get started. We're going to look at cylinders, we're going to look at spheres, we're going to look at how we can deform and move these things around, which are all fairly simple ideas that we can connect to stuff that you have seen before, because in fact you have seen a cylinder before in the first presentation on three-dimensional coordinates, I think. Alright, so if I want to describe a cylinder of radius r around the z-axis, what would I want to do? The standard parametrization, and this is a parametrization that is worth memorizing, is surface of theta and z being r cosine theta, r sine theta, and z. So r is a constant, and that is the radius here, and we can already, with what we know from vector-valued functions, realize that that does make sense, because when r is a constant, then r cosine theta and r sine theta describes a circle of radius r, and that circle of radius r then by this third coordinate z is put to various heights z, and if you've got a circle of radius r that moves up and down the z-axis, well, that traces a cylinder. We will have theta going from 0 to 2 pi, because we want to have the whole circle certainly and whole cylinder, and that makes sure that we draw a circle. And bottom smaller equals z, smaller equal top, that just limits the cylinder to a bottom and a top if we want to have that. Technically z could also go from negative infinity, but b would be the bottom, t would be the top. How do we draw that? Well, x, y, z, right-handed coordinate system, right? We have a circle, and in fact we don't have just one circle, but we've got a bunch of circles at various heights z, and they are connected, and that gives us a cylinder, as we can see here. And the cylinder has radius r, so the radius is here. And if we want to look at an arbitrary point on that cylinder, and note now that this vector-valued function must give us the position vectors of arbitrary points on that cylinder, the way that happens is that the third coordinate, the z, is right here, that's this z, and then this distance here, of course, because that's a circle, this distance here is the same r as before, and this angle here is the theta from up here, and so that's exactly what we've got. R cosine theta draws circles at various heights, and the z just tells us at which heights these circles are supposed to be drawn to get the whole cylinder, which is either limited vertically or unlimited. It could be an infinite cylinder around the z-axis. All right, so this is definitely something worth memorizing, because this is also the idea for cylindrical coordinates, which we will also look at very shortly. As I promised you, we will revisit these things. We will look at them from slightly different points of view. This point of view is that we just want to draw cylinders. Cylindrical coordinates will allow us to express points in 3 dimensions in other ways than just x, y, and z. Well, how could we play with this? Well, one of the things that we could do with a cylinder is we could make the radius a function of z. So we could have something that then is sort of like a vase that has been done by a potter on a spinning pottery wheel, or it could be something like a turned component that has been made on a lathe. And of course, those things we have already talked about as surfaces of revolution. Well, first, I'm getting ahead of myself. Here's how we draw that cylinder, right? So we've got the theta, which draws the circles. We've got z, which draws vertical lines. And once we interpolate the whole thing, we've got the cylinder, right? Okay, so now how can we play with those things? Well, we could make the radius a function of z, which would give us something like a turned component, something that has rotational symmetry. And that's a fairly standard parametrization, or a fairly standard idea, actually. So varying the radius could turn a cylinder to something like a vase, and then, of course, it could also come back like that. Well, how do we do that? Okay, so to model cylindrical objects, what we would use is a parametrization S of tz being f of z cosine t, f of z sine t. That gives us a circle at height z that has radius f of z, which means it does exactly what we showed in the previous animation, and that is that the radius varies with the height. Now t goes from 0 to 2 pi, and then lower bound is less than or equal z, is less than or equal than the top bound here, and that parameterizes this cylindrical object, with horizontal cross-section being given by f of z and extending in z from L to t. And that's exactly what we have already seen in solids of revolution, because basically what this is that we have a function where the radius depends on z, so that's a function that actually is drawn in the upwards direction, and then that function is rotated by cosine t sine t around the z-axis. All right, so the parametrization of a cylinder you definitely want to memorize. This one, I'm not sure if that's worth memorizing, because if you really understand how a cylinder works, then you can easily reconstruct for yourself how you vary the radius to get these round objects here, these turned components. Okay, and so that is exactly what we saw for volumes of revolution, right? So we can now model the surface of a volume of revolution. Another standard object are spheres of radius rho centered at the origin. Here's the parametrization. It's certainly something that you want to memorize, because it's also at the heart of spherical coordinates, which we will also revisit very shortly. Theta goes from 0 to 2 pi. Phi goes from 0 to pi, and yeah, we probably want to talk that one over. And basically what we have is we have a situation where, again, we have theta being basically the same angle as for cylindrical coordinates. So we've got cosine theta and sine theta, making sure that we draw stuff that has circular horizontal cross sections. And at rho sine phi, well, or at whatever phi encodes, rho sine phi is the radius. So this certainly is something that has rotational symmetry along the z-axis, and that certainly is something that a sphere that is centered at the origin has to have. The connection between z and the radius isn't quite clear, but we can see that if we take this radius and square it and add it to the square of z, we get rho squared sine squared phi plus rho squared cosine squared phi, and that's equal to rho, which is the radius, which does make sense because that rho sticking out plus the z, that ought to give us the distance to the origin. And so that means what this actually looks like, x, y, z, right-handed coordinate system, is that if we've got a sphere here, here's the origin, here's a point. This is the distance from the origin, and that is rho. Visually speaking now, our angle phi is actually an angle of the z-axis. And if you work that out then you can realize, and we're going to work that out explicitly when we talk about spherical coordinates, that then z really is rho cosine phi, because let's see, this angle phi also arises in a right triangle here. Phi would be right here because it would be angles on parallel lines, and so z over rho would be cosine phi, so that means z is rho cosine phi. Then if we're looking at r, this is the radius r from cylindrical coordinates. It's in the same right triangle, and if phi is up here, then the radius is rho sine phi, and then of course rho sine phi gives us the radius for what we need in the cylindrical type setup up here, and theta is still the angle that we know from cylindrical coordinates. Alright, this picture is another one that you want to keep in mind. What I typically remember is I want to understand what theta does. It's projecting down, and then it's the angle like in cylindrical coordinates, and you want to remember that phi is coming off the z-axis. And that would be s of theta and phi. And if we want to draw a sphere of radius 1, well, okay, the theta stuff draws circles, and the phi stuff, as you can see, phi comes off the z-axis and draws these long half circles. That is also why theta has to go from 0 to 2 pi, because theta has to take care of the whole rotation around the z-axis, whereas phi only has to go from 0 to pi, because once we've got all those circles, the longitudes only need to go over 180 degrees, not 360 degrees. All right, so that is what these coordinates do. Thetas are the reds, and phi's are the blue ones as they vary. What can we do with a sphere? Let's play with a sphere a little bit. Okay, so a sphere has three coordinates: an x-coordinate, a y-coordinate, and a z-coordinate. If I now go ahead and vary the radius in each of these directions, and we could do that, well, then I could squeeze the sphere, stretch the sphere in the x direction, in the y direction, or in the z direction. So if I take a parametrization of a sphere and I multiply the x-coordinate with rx, the y-coordinate with ry, and the z-coordinate with rz, then I can stretch and compress that sphere in the x direction. Here's where rx varies. In the y direction, here's where ry varies. And in the z direction, that is where rz varies. And that means I can use that same parametrization to also encode things like ellipsoids, for example. And so that's something that we just want to keep in the backs of our minds. And we can also shift objects around. So say I want to have a sphere, but I want it to be centered at the point cx, cy, cz. Well, if I just add a vector, well, at vector addition just tacks a vector on and moves the object, right? So if I've got a bunch of points here, then if I tack the vector cx, cy, cz onto every one of those points, then that gives us, with 0 being less than or equal theta less than or equal 2 pi, and 0 less than or equal phi less than or equal pi, that gives us a sphere that is placed at cx, cy, cz. So we can move the sphere or any object we want in the x direction, in the y direction, and also in the z direction. So you can see here that we have a large a large number of ways to move objects around, so that we could potentially also then, with multiple surfaces, represent multiple objects in space, such as multiple spheres. And what you want to remember really is you want to have the parametrization of a cylinder internalized, you want to have the parametrization of a sphere internalized, and you want to understand vector addition. Once you understand vector addition, you realize, yeah, shifting things around is just adding another vector. And then as you understand spheres and cylinders better, as we keep moving through this course, you realize that as you vary radii or put various factors into a sphere, you can also represent other objects. We conclude with the simplest standard representation in parametric surfaces whatsoever, and that is a function z equals f of xy. We can simply take surface of x and y being xy f of xy, where xy ranges over the domain of the function, and that would give us, if we get a regular right-handed coordinate system x, y, z, we would still have the domain, and we would still have the function up here. It's just this time it's the domain of the parametrization, and so now if we take an xy and plug it into the function s, we end up with this point, which has position vector s of xy being xy f of xy, in this way of visualizing the graph, because now we are not talking about the graph of a function but a parametric surface we're not going to project over. We just realize that the value of the vector valued function actually is just xy f of xy. This is going to be very helpful because, again, for various geometric properties we are going to work with the surfaces, and if we want to have formulas that apply to functions, which are not bad to have, we are simply going to use this parametrization for the surface in order to work things out. This is very similar to how we encoded functions of one variable as vector valued functions with values in two-dimensional space as x, comma, f of x, right? Okay, so now let's take a look at a few examples of things that we can do with surfaces. For example, somebody might just tell you to describe a parametric surface given by surface of u and v being u cosine v, u sine v, 9 minus u squared, where u goes from 0 to 3 and v goes from 0 to 2 pi. Okay, so here's where we're definitely at the pinnacle of visualization skills. Somebody just gives you something and you're supposed to tell them what the geometric object looks like in three-dimensional space, but I claim we can handle that. We just have to remember that when we look at parametric surfaces, it's always good to just hold one of the variables constant and then let the other variable vary. And so if I hold u constant, I realize I get a circle because cosine v sine v describes a circle multiplied by u. It's a circle of radius u, and the circle will be at height 9 minus u squared. So this is something with circular horizontal cross sections, so it's symmetric around, and it's symmetric around the z-axis, and then the z is 9 minus u squared, and the u squared is essentially the radius that we have. So this is something with circular cross sections where the height is 9 minus the radius, which means that for radius 0 we get a point at height 9, and then as the radius increases we get larger circles that go down, so this ought to be something like a paraboloid. Okay, so let's see how I talked my way through that in writing. The first two coordinates describe a circle of radius, u, okay. The z-coordinate only depends on that radius, and so the surface should be a shape that is symmetrical with respect to the z-axis, just like we said. And because z of uv is 9 minus u squared, it should be parabolic, opening downwards, and you want to visualize that mentally, right? I've talked you through it. We're also seeing it here. Remember, this ought to be a u. And, well, now let's take a look if that really is what we said it is. Here's the sketch. Okay, we're first letting the u vary. That gives us these half paraboloids. And if when we let the v vary, we get the circular cross section. So it's exactly that paraboloidal shape that we have, that I promised you. And, well, it's basically 9 minus u squared. As u goes from 0 to 3, that's this downward opening half parabola because u is greater or equal than 0. And then the circles, of course, those are pretty easy to buy in this surface. All right. What else can we do? Well, sometimes when we have a parametric surface, we might not be able to really see what the surface looks like. And it can then be very helpful to find the Cartesian equation for that surface. And in order to do that, it is often helpful to use pattern recognition. So for example here, I already know that u sine v, u cosine v, yeah, that encodes a circle. And we know that in order to get rid of sines and cosines, squaring and adding is always a good idea. That's also a good idea because the equation of a circle involves x squared plus y squared. So we might as well take u sine v quantity squared plus u cosine v quantity squared and see what that gives us. Well, it gives us u squared sine squared v plus u squared cosine squared v, which is u squared, and we realize u squared is z squared, u sine v is x and u cosine v is y, and so this means this is x squared plus y squared equals z squared, and that's already it. So this is actually the equation of a cone, and this is a part of a cone model. This is how we model a part of a cone. We're going to see the pictures a little bit later on because we're going to do something with this cone also. So another example, for the part of the graph of f of xy equals 36 minus 9x squared minus 4y squared. So that's an elliptic paraboloid. We're going to talk about these things in more detail when we talk about quadratic surfaces. So again, if that vocabulary isn't familiar to you, don't worry. Right now it's just a graph, and it's parabolic opening downwards because it's got the minus x squared and the minus y squared, right? So for the part of that graph that is above the xy plane, we want to find a representation as a parametric surface, and importantly, with rectangular domain, because ultimately we will want to integrate over those kinds of things, and then having a rectangular domain will be advantageous. Okay, so f of xy has to be greater or equal than 0. That means that 36 minus 9x squared minus 4y squared must be greater or equal than 0. Well, that means that if we bring the x's and y's over and then just switch sides, we get that 9x squared plus 4y squared must be less than or equal than 36. Well, that sort of looks like the equation of an ellipse. Let's divide by 36. We end up with x squared over 4 plus y squared over 9 is less than or equal than 1. So yeah, that is basically the equation of the interior of this ellipse. X squared over 4 plus y squared over 9 equal to 1 would be the ellipse, and the interior is given by the less than or equal. Well, if I set my x of t to be 2r cosine t and my y of t to be 3r sine t, well, then I am tracing circles with distorted radii, which is what ellipses are, and the 3 squared cancels with the 9 and the 2 squared cancels with the 4, so this definitely has a chance to work out. If I let the radius run from 0 to 1, I get stuff where this just adds up to stuff that is less than or equal than 1. You can work that out with paper and pencil. And so we've got 0 less than or equal r less than or equal than 1, and 0 less than or equal t less than or equal than 2 pi, because we're going all the way around. And z of t then is f of x of t and y of t, and that's something that we just have to plug in. 36 minus 9 times 4 r squared cosine squared t minus 4 times 9 r squared sine squared t. Well, 9 times 4 and 4 times 9 are both 36. So we end up with 36 minus 36 r squared cosine squared minus 36 r squared sine squared. Cosine squared plus sine squared of t is equal to 1, so that's just 36 minus 36 r squared. And that is the parametrization, because now I can just stick that in. I've got the parametric equations, and now I could just put that into a vector also and say 2r cosine t, 3r sine t, 36 minus 36r squared. And yeah, if you want to, hit pause right now, plot this in a computer algebra system, and see that you really get the same graph both ways. Another example about intersections. Intersections will ultimately be important because we will model all sorts of solids by modeling their boundaries, and then of course in order to get exactly the right cutoffs we have to find the intersections between these solids. So here I want to find the intersection of this cone v cosine u, v sine u, v, u going from 0 to 2 pi, v going from 0 to 10, with the ellipsoid 3 cosine u sine v, 3 sine u sine v, 6 cosine v, u going from 0 to 2 pi, and v going from 0 to pi. Well, let's see, what do we have here? This is similar to what we did with the cylinder, right? Except that the radius is the same as the z-coordinate, and if the radius is the same as the z-coordinate, you do get a cone. This parametrization is very similar to what we had for a sphere, except that we've got a radius 3 in the x and y direction and a radius 6 in the z direction. So this is an elongated sphere, which is an ellipsoid. And well, if we now want to find the intersection, we have the same problem as we did for vector-valued functions of one variable, and that is I can't just set cuv equals to euv, because that would just give us the points where the various parameters are equal and the outputs are equal. So I would actually have to say something like cuv is equal to e of s and t, and I would have to work with 4 variables, and that gets really messy. So for intersections, it is usually very beneficial to first, so instead of solving CUV equals EST, it is usually preferable to first convert to Cartesian coordinates. Okay, so what do we obtain for the cone? Well, we square the x and y coordinates because we know that squaring gets rid of cosines and sines, right? And so that's a good thing to try at least. And if it doesn't quite work out, we can always tweak it. So we get v cosine u quantity squared plus v sine u quantity squared. That's v squared cosine squared u plus v squared sine squared u. Factor out the v squared, and we end up with v squared. So that's x squared plus y squared equals z squared. Right, yeah, we basically just did that in an earlier example, but oh well, this is another thing that is really not bad and certainly left in here deliberately because after all I prepared those slides in advance. The idea is that every so often in the heat of battle, if you will, you might duplicate a computation, but there's nothing wrong with that. What you want to be able to hang on to are the ways in which you figure things out, because once you know that, you can always do the computation again. So that is a lot better than trying to memorize a lot of stuff about cones and other things. For the ellipsoid, well, for the ellipsoid, let's see, we probably want to try the same thing. We want to square to get rid of the cosines and sines of u, and that'll give us sine squareds of v, and so if we square this one here, then we also have a cosine squared v to get rid of things. And we need to adjust that a little bit because 3 squared is 9 and 6 squared is 36. So 9 times 4 is 36. So I probably want to have 4 times the x plus 4 times the squared plus 4 times the y squared plus the z squared. And so that's exactly what I've set up here. And that's, of course, now 4 times 9 is 36, cosine squared u, sine squared v. 4 times 9 gives us 36, sine squared u, sine squared v. 6 squared is 36, cosine squared v. If we now factor out a 36 sine squared v out of the first and out of the second term, all that is left is cosine squared u plus sine squared u, so this just is 36 sine squared v plus, of course, we have to keep the last term, and we happily do so. But 36 sine squared v plus 36 cosine squared v is 36. And so that means that for the ellipsoid, we obtain the equation 4x squared plus 4y squared plus z squared equals 36, which we will pull over because now we have the two equations. The cone is x squared plus y squared equals z squared. The ellipsoid is 4x squared plus 4y squared plus z squared equals 36. And now, well, we've got a system of nonlinear equations, and those things have no hard and fast rules how to be solved. We use pattern recognition, and we realize that, well, 4x squared plus 4y squared, that's just 4 times what we've got up here. Or I think what I'm going to do is I'm going to substitute x squared plus y squared in for z squared. Yeah, 4x squared plus 4y squared plus z squared being x squared plus y squared is 36. So that means 5x squared plus 5y squared, of course 4 plus 1 is 5, we're doing deep mathematics here, is 36. And so that means x squared plus y squared is 36 over 5, and that is now really a circle. The intersection of two surfaces typically is a one-dimensional object. That 36 over 5 is the z squared, because after all x squared plus y squared was z squared. So that means that z is plus minus square root 36 over 5, and that is plus minus 6 times root 5 over 5. And that would mean now, because our cone, the part of the cone that we're interested in, looks at positive v's, that means that only z equals 6 times root 5 over 5 actually plays a part in the whole thing. And the intersection, therefore, then is 6 times root 5 over 5 cosine t sine t to incorporate, encode the circle, and 1 gives us the height in z. As a picture, here's the cone, here's the ellipsoid, and here's the intersection. Well, let's take a look at that. I squeezed that here a little bit because I wanted to have it all in one picture. You can see the disadvantages sometimes of working with column vectors, but certainly that's something we can also take a look at and rotate around a little bit. Here's the same picture. We've got the cone, we've got the ellipsoid, here's the intersection. We can certainly see that if we look at this straight down from above, that the intersection really is a circle. And if we look at it from a horizontal point of view, we also see that the intersection really is constant in z. And of course, now the neat thing about this part of multivariable calculus is that the pictures and the equations really are in very nice one-to-one correspondence. All right, so now I think we move on. Yeah, let's look at that. That was just my reminder for myself to go to the MathCAD file. And now, finally, we're going to talk about boundaries of surfaces and solids. Boundaries of objects will be very important when we investigate theorems for surface areas, for surface integrals. And so we are looking way ahead right now. However, these results, which are the divergence theorem and Stokes theorem, are the pinnacle of this calculus course and of pretty much any calculus course. They are very important. They are fundamental for physics because they are the mathematical manifestation of important physical phenomena. And so even though we're looking a good way ahead, it will help in the long run because the integral theorems won't seem quite as challenging as otherwise if we have to do all the visualization and then jump into the integral theorems. Of course, the price that we're paying is that we are really here at total immersion right now, and we're going to look at intersections of surfaces now, or boundaries. So if we're looking at the paraboloid f of xy equals 7 minus x squared minus y squared, I want to parameterize the boundary of the part that lies above the plane z equals 2x plus 2y. Okay, well, the first thing we have to do is we have to find the intersection, and here we actually have z equals something depending on x and y, and here also z being something that depends on x and y. That is something we actually can set equal to each other because those are just Cartesian equations. So we get 7 minus x squared minus y squared is 2x plus 2y. That means if I bring the stuff with x's over, I get x squared plus 2x plus y squared plus 2y equals 7. So I brought the x squared and the y squared over and then flipped sides. And, well, I can complete the squares here again, right? And in fact, the terms that complete the square are pretty simple. We have to add 1. And I'm going to add 1 on both sides. So I've added 1 here, as well as here. And of course, if I add that 1 twice to 7, I get 9 on the right side. And now this ends up being x minus 1 quantity squared, x plus 1 quantity squared, and this being y plus 1 quantity squared. And that's the equation of a circle of radius 3 around the point -1, -1. Okay, to get a circle, I set x of t to be 3 cosine t minus 1 and y of t being 3 sine t minus 1. Basically, the center is therefore -1, and we are rotating with radius 3 around that center. So this is very similar to the shifting that we mentioned earlier in this presentation, only in 2 dimensions. And the z-coordinate, well, the z-coordinate, I can use either the f of xy or the plane, and I'm going to use the plane because that's easier. Well, 2x of t plus 2y of t, that'll be 6 cosine t plus 6 sine t minus 4, right here. And so that means that the curve as a vector-valued function of one variable, the intersection would be 3 cosine t minus 1, 3 sine t minus 1, 6 cosine t plus 6 sine t minus 4, and that would be this situation. Here's the paraboloid, here's the plane, and here's the intersection. Let's take a look at that in something that we can rotate around because we had mentioned circles. Okay, I have to go to the other sheet. Okay, here's the same picture as what we had. I claimed that there was a circle involved, and that is correct because if we're looking at just x and y without the z influence, well, if we're looking straight down the z-axis, we realize that this thing really looks like a circle. It's just that when it is being put on a plane, it stretches out and becomes a more elliptic shape. And we can also see that the z ultimately is just something that sits on the plane here. All right, so that would be the boundary of that intersection. And, well, the boundary of the part that lies above the plane, because the part that lies above the plane is this little cap here, and here the boundary is that intersection. Okay, finally, or close to finally, I think, we want to parameterize the boundary of the solid cylinder that is given by x squared plus y squared less than or equal than 9, and 1 smaller equal z, smaller equal 8. Well, we know what a cylinder looks like, right? And that is that a cylinder looks like this. However, if we want to be completely honest with ourselves, well, if we want to look at the whole solid cylinder, the parametrizations that we have discussed is just a parametrization of the walls. However, a cylinder, of course, also has a top. We don't look inside here, right? And a cylinder also has a bottom. And so that means this is actually an object where we need to parameterize the boundary in 3 different pieces: sides, top, and bottom, which should be familiar to us because that's also what we did when we were optimizing the shape of a soda can, for example. So the sides, well, the sides are the standard parameterization. So that's something that you ought to remember very quickly, and that is if the radius is 3, then the sides are 3 cosine theta, 3 sine theta, circle of radius 3, placed at height z with z in the third coordinate, theta going from 0 to 2 pi, z going from 1 through 8. And then we have the top. Well, what do we know about the top? The top is at z equals 8, and it's a solid disk. And a solid disk is nothing else but a bunch of concentric circles, right? That's also what we have seen here. This solid disk is just a bunch of concentric circles, and if we have enough concentric circles, then these things make a solid, right? And so the top should be a solid disk. Okay, how do we get that solid disk? S of theta and r is 3r cosine theta, 3r sine theta, and 8. Well, we know that the top is at height 8, so z equals 8 is okay. Cosine theta sine theta multiplied by 3 gives us circles of radius 3, and I put the r in there going from theta from 0 to 2 pi and r going from 0 to 1. That gives us concentric circles from radius 0 to radius 3, ultimately, because it's 3r here, and those are exactly the concentric circles that we can see here on the top of the cylinder. Bottom should work the same way, right, because the bottom is a solid disk, which can be seen as made up also of concentric circles. So we set up the bottom as S of theta and r being 3r cosine theta, 3r sine theta, and 1, because the bottom is supposed to be at height 1. Theta goes from 0 to 2 pi, and r goes from 0 to 1 here. That is just a matter of personal preference. I could have also dropped the 3's here and then made r go from 0 to 3. That may have been a bit more natural, actually, but both types of parametrizations actually work equally well, and that is just an indication that sometimes, as I've also mentioned earlier on, sometimes a solid becomes more complicated and we need to describe it with its boundary with multiple surfaces. Alright, you've made it through a lot of visualizations. We first talked about the functions of several variables. Now we have talked about the parametric surfaces. As I promised, the idea is simply to give you total exposure of everything that's there so that your mind can get started on making some, maybe even subconscious connections. I've told you there are a couple of things you want to memorize here: parametrization of a cylinder, parametrization of a sphere, chief among them. Then there is a good bit of algebra that we have done here. And, well, now it is time to certainly, again, for you to do some homework on this stuff, and otherwise in the next presentation it's going to get, just like we did for the vector valued functions of one variable, it's going to get a bit simpler because we're going to take a look at flat objects, we're going to look at planes, and I think a slightly simpler setup is in order because we've pushed pretty good. So I'll see you for the planes.